Okay, so this week we're talking about linear systems and also talking about word problems. So a linear system is when you have two or more linear equations that you talk about at the same time, or you consider them at the same time or simultaneously. So if you draw them on the same graph, that becomes a linear system. So as soon as you have more than one line. So there are three different ways that lines can interact. You can have parallel lines. And if you have parallel lines, these are lines that never cross. So they'd have the same slope. And there's no point that satisfies both equations. I'll talk about more of that in a second. But what we say is that there's no solution. And the solution is when you have two non-parallel lines and they intersect. So there's a point of intersection. This one specifically, they intersect at 1, -1. So that has one solution, and that solution is the point. When you have two identical lines, so if I were to graph these on the same graph, they'd be right on top of each other. They'd look like the exact same line. Now, the equations look different, but they describe the same line. What we say there is that there's an infinite number of solutions because they're always intersecting. You have two lines that would be right on top of each other. So they're always touching, which means that there's an infinite number of points of intersection. So there's an infinite number of solutions. So let's see what this looks like when we graph. So I have two equations here. Y is equal to 1 over 2x minus 3. And x plus y equals -6. And we want to graph these and then see where they intersect. And that would be our solution, point of intersection. So let's look at the first one. So you're going to remember how to graph equations. Sorry if you can hear my kids crying in the background. So first we start with our y-intercept. Y-intercept is -3. So you go to -3, you plot your point. What's in front of the x is our slope. And that tells us how to move, our rise and our run. So we go up 1 from the y-intercept, the point that we have. Right? It could be any point, but we know the y-intercept. So we go up 1 from there and right 2. So up 1, right 2, there's a new point. And we could keep doing that. And I recommend you do that a few times. Going back and forth so that you get an accurate line. So that's the first line. Now let's look at our second line. X plus y equals -6. Now there's a couple ways that we could graph this. You could do a table of values. That's the easiest way. It takes longer, but it's easier. Another way is to find the x and y intercepts. That would also be pretty easy. But since we're talking about solving equations, let's solve the equation. So I want to get y by itself. I want to get y equals something, which means I want to get rid of that x. So the way to get rid of the x is to the opposite of it, -x. So x minus x is 0. I'd have y equals -x minus 6. They're not like terms, so I can't do anything with that. And I have it in y equals mx plus b form, slope y-intercept form now. So this is our y-intercept, and this is our slope. So I go to y-intercept. Let's make this one purple, I guess. And I plot a point. And now I look at the slope. So the slope says -1. That's the coefficient that's in front of x, right? We have -1. So let's see, we can go down 1 and right 1. Or you can do the opposite. You can go up one and left one. It just depends on what's going on with your graph. So here, if I go down one and right one, I'd run out of space. That'd be a point down there. So I can do the opposite. Go up one, left one. I could keep doing that, and if I do that, we can see that we have a point of intersection there. Just going to graph the line. So our point of intersection is right there. And the coordinates for that would be -2, -4. So the point of intersection, or POI, is -2, -4. So we call it the POI for short. It takes too long to write point of intersection every time. So it's the POI. And that's my son screaming his head off. So -2, -4 is the only point that would satisfy both equations. If I plug in -2 for x, I found that x is -2. If I plug it in there, that whole equation would be equal to -4. If I take -2 and I plug it in here, or I plug it in here, it doesn't matter, y would be equal to -4. So for both equations, if x is equal to -2, y would be -4. But anywhere else along those lines, it wouldn't be true. For instance, over here, when x is 4, y should be -1. So that works for this equation, but does not work for that equation. If you plug in 4 here, you do not get -1. You get -10. Because if I plug in x is 4 and I go all the way down here, and when I would hit that purple line, it would be -10, somewhere down there. So any other point would not work. This is the only point, that point of intersection, that would work for both of those equations. So now let's look at some word problems here. Word problems and graphing at the same time. So we have two situations here. This couple is getting married. They have $5,000 for their wedding reception. We're trying to figure out which hotel offers the better deal and under what conditions. So they have two options, the Waverly and Hotel Niagara. Let's first talk about Waverly Inn. So if we're talking about the cost in dollars and N guests, the cost for Waverly is $1,500 plus $40 for every guest. So we would multiply by the number of guests. For Niagara, it would be $1,000 plus 50 per guest. So let's see what that would look like if we graph it. So we're going to use a table of values here now. I should have done two columns, so I'm going to split that up. I'm going to put Waverly here. Oops. Sorry. I'm going to put Waverly here, and we'll put Niagara over here. So 0 guests, 20, 40, 60, 80, 100. I'm just taking what's along the bottom of the graph there. So let's do Waverly in green. So if 0 people show up if they choose the Waverly Hotel and nobody shows up, they had to put down a deposit of $1,500. So it's going to cost them $1,500. Now for every 20 people showing up, it's going to cost a certain amount, right? So if we take that 20 and I plug it in for the number of guests, I'd be doing 40 times 20, which is 800, plus 1,500 to get $2,300. Now to figure out the next, I would take 40 and plug it in for n. So we're multiplying 40 times 40 guests is 1,600 plus 1,500 is 3,100. Okay, you can see that it's going up by the same amount, right? It's going up by $800 each time. So if you did it again, you could just add the difference, or the first difference, but 60 I put in there. So 40 times 60 is 2,400 plus 1,500 makes 3,900. Adding 800 each time. So if I add 800 again, I would get to 4,700. And we're getting close to our max, right? Their budget is 5,000. So if I add another 800, I get to $5,500, which is over their budget, but that's okay. It's good for a graph. So now let's do Niagara in purple here. Niagara, nobody shows up. It's $1,000. And now for every guest that shows up, they have to pay $50 per guest. So if 20 people come, we're gonna do 50 times 20, which is 1,000 plus 1,000 makes $2,000. You can see I added 1,000, right? So I'm sure you can guess what would happen next. If you can't, what you're doing is taking the 40, multiplying by 50 to get 2,000, then adding 1,000 so you get 3,000. So yes, we are adding 1,000 each time, and then we're over budget by the time we get to 100 guests. So it looks like if they choose Niagara, they can only have 80 people at the wedding. So let's graph both of these things. First, we'll do Waverly. So 0 people show up, $1,500. So that's our y-intercept, our initial value. If 20 people show up, we have 2,300. So it's not exact, but close enough. 40, 3,100. Again, you got to estimate a little bit, but that's okay. 60, 3,900. 80, 47. And 155, which goes off the graph. So this is our approximate graph. And now for Niagara, if 0 people show up, it costs $1,000, and increasing by 1,000 for every 20 guests. So 20 was 2,000, 40 was 3,000. Let me do that again because it's slightly under. It looks like it's intersecting, but it's not. 60 is 4,000. It's just a little bit over. 80 was 5,000. Okay. So, as we can see here, it looks as though at 50, approximately, we have a point of intersection. 50, 3,500. Now, this could be an estimate. It may not be the right exact answer that we would find algebraically, but according to our graph, it's what it looks like. So what does it mean? Our point of intersection is 50, 3,500, and you write it as a like that, an ordered pair in brackets with comma in between. And what does it mean? Well, if 50 guests attend, it will cost $3,500 at both hotels. So it doesn't matter at that point if you take the Waverly or the Niagara. But if you have less than 50 people coming, you would pick one versus the other. If you have more than 50 people coming, then you'd pick one hotel versus the other. And I'm going to leave that for you to figure out. If you look at the graph, you should be able to figure that out. It says determine the point of intersection algebraically, and we could do that. I just don't want to overwhelm you with all this stuff at this point, so I'm going to skip that part, and maybe we'll come back to it another time. We'll see how everything goes. Now we're going to move on to word problems and how to take language and turn it into algebra. So I have here Greg is 42. He's 3 years older than Sue. Not exactly a difficult thing to figure out. If Greg is 42 and he's 3 years older than Sue, then Sue must be 39. But what we're practicing here is taking that and turning it into algebra. So first thing we need to do is determine a variable. What's the thing I don't know? We figured it out, but pretend we didn't figure it out. We didn't know how to subtract 3. Sue's age is the thing that I don't know. Right? That's what we have no idea about. So we would create a variable for the thing that I don't know, the thing I'm trying to figure out. So I'm going to say let S represent Sue's age. So Sue is equal to Greg's age minus 3. Now, I could put 42, but that's not really an equation with variables and stuff. So I'm also going to do, in this case, a variable for Greg, but then we're going to substitute it in. So just to make it make sense, let G represent Greg's age. So it's going to be Sue's age is Greg's age minus 3, since he's 3 years older than Sue. We could also say that Greg's age is equal to Sue plus 3. Either way, it works. Right? It's almost like we just rearrange the equation. So, how old is Sue? Well, let's pick the first one. What's Sue's age? It's Greg's age minus 3. Now, since we know Greg's age, I would substitute that in, and she's 39. Okay, again, not exactly something that we'd really need an equation for, but I'm just showing you how you would take language and change it into algebra. Now, the next one is harder. So it's going to take a minute. You might want to have to pause the video and just read the question over. Try to understand it before I go into it. The total of 3 sisters' age is 39. Dina is half as old as Michelle and 3 years younger than Juliet. How old are the sisters? Now, your temptation here is to make 3 different variables. One for Dina, one for Michelle, one for Juliet. And you could, but the problem is if you have 3 different variables, you can't solve. You can't figure out what they are. You need to have one variable. At this point, later on when you get more advanced math, it changes. But right now, we only want one. So what we want to do is pick one of the sisters and show their age or all the other sisters' ages compared to that one sister. So I'm going to pick Dina because she came first. I'm going to say that let Dina, D, represent Dina's age. Okay, so D is Dina. So that's the thing I don't know, right? I don't know Dina's age, but I know that Michelle is something compared to Dina. I know that Juliet is something compared to Dina. So if D is Dina's age, let's look at the rest. Dina is half of Michelle's age. Okay, or another way to say that is that Michelle is 2 times Dina's age, or 2D. You could also say, since the last thing says that Dina is 3 years younger than Juliet, so Dina is Juliet's age minus 3. Or we could express Juliet's age as Dina's age plus 3. So if Dina's age is D, let me just write this here. Dina's age is represented by D. Michelle's age compared to Dina's 2D. And Juliet's age is D plus 3. If I take all those and put them back together, I know that all of their ages added up is 39. So Dina plus Michelle plus Juliet. Is there 2 L's in Juliet? 1 L in Juliet. Sorry, Juliet. Spelled your name wrong. I know that that's equal to 39. But now I have 3 different things. I don't know what each one is. But I do know that D is Dina. Michelle is 2 times Dina's age. And I know that Juliet is Dina's age plus 3. So now I've shown all their ages just compared to one of the sisters, just Dina. So now I can solve this equation. 1D plus 2D plus D. That's 1, 2, 3, 4 D's. Right? 4 times Dina's age plus 3 is 39. So I'll solve for D now. Dina's age. Subtract 3. 4D is equal to 36. I wrote too big. So now we're going to do divide by 4. So D is equal to 9. So D is equal to 9. Just make some more space here. Oops. Try that again. Don't worry, I'll figure this out eventually. All right, so what did we figure out? Therefore, Dina is 9. So then Michelle is 2 times Dina's age, or Dina was half of Michelle, so Michelle is 18. Juliet, however you spell her name, was Dina's age plus 3. So she must be 12. Okay, so these word problems take practice. I've included some practice down here. Please go over 1 to 10 if you have time. So that's practicing what we did, or 1 to 11 actually. That's what we had done last week, but it's good to review that because you need to know it. And it's going to be on our assignment for this week. And try to go over these word problems. The answers are here, so you should know if you got it right or not. Okay, see you